Hey everyone, in this video we are going to talk about the architecture of generalization. So look at this picture. On the left we have a finite set of training points and on the right is the entire unseen reality. So the learning algorithm draws lines from the training data outward and the question is how far can those lines go before the error becomes large? So statistical learning theory gives us mathematical tools to bound that error and that is the architecture of generalization which we are going to study. Now there are two numbers we care about, empirical risk and true risk. So empirical risk means how well the hypothesis perform on the training sample and true risk means how well it would perform on the entire distribution. So we choose the hypothesis that minimizes the empirical risk and the central question becomes how close is true risk to the empirical risk. Okay. Now, then moving on forward, we see a generalization gap. As model complexity grows, training error can go to zero, and true risk usually become like rise. So the difference between them is the generalization gap. So statistical learning theory exists to bound this gap mathematically. We need to prove that low training error is not an illusion. Okay. Now PAC. PAC learning has two parts. First is probably means the guarantee holds for most training samples with confidence 1 to delta. Okay, and then second is approximately correct. So the true risk is written in epsilon of the target. Okay, within the epsilon of the target. So, if the sample size is large enough, then write high probability. The true risk is at most epsilon. Okay, we can say like that. Then bounding finite hypothesis classes. So start with one fixed hypothesis. Hoiferding inequality bounds the deviation between true and empirical risk. And to protect every hypothesis in a finite class at once, we use the union bound. So the final resulted true risk is less than equal to empirical risk plus a term that grows with the log of the class size and shrinks with the square root of the sample size. Right. Now we see an example. Suppose the hypothesis class contains all Boolean functions on 100 bits, like 2 power 100 functions. So we have 1000 samples and want 95% confidence. So like we plug the numbers into the bound, the gap is about 0.19. Even for a huge class, 1000 samples already give a useful guarantee. Okay. Now we see infinite problem. So many useful classes are infinite. All lines in the parallel, for example, we can no longer count the number of hypotheses. So instead, we measure the largest number of points the class can shatter, perfectly separate under every possible labeling. That number is a VC dimension. So for linear classifier in 2 dimension, the VC dimension is 3. Okay. Now we see generalization bound. So the finite class bound is replaced by a bound that depends on VC dimensions. The growth function of the class is at most like in end party. So the result generalization gap scales like the square root of this, right? It's written here. So the complexity is now measured by geometry, not by a log cardinality. Okay. So that's all. Then comes VC dimension on common classes. So threshold functions have VC dimension 1. Intervals have VC dimension 2. Convex polygons with k sides have VC dimensions 2k plus 1. Sine waves have infinite VC dimensions and are not PAC learnable. And deep ReLU networks have large but finite VC dimensions. So the bounds are usually too close to be useful. Okay. Now, excess risk splits into two parts. First is approximation error, which decreases as the hypothesis class grows richer, and second is estimation error, which is variance. So, which increases with the square root of the complexity over sample size, and this is an optimal complexity that balances the two, and that is the classical bias variance trade-off. Now, in the realizable versus agnostic. So, in the realizable case, a perfect hypothesis exists inside a class. So, sample complexity scales linearly with the 1 by epsilon naught, and the agnostic case, the best hypothesis may still have residual error. So sample complexity scales with 1 by epsilon naught square. So the real data is most all like real data is almost always agnostic. So we need far more samples, right? Now the neural network reality check. So a modern network can have VC dimension on the order of 1 million. To guarantee 1% error with high confidence, the classical bound asks for roughly 10 billion samples. So the bound is correct but usually uselessly loose. So to explain why deep networks generalize, we need a bit what we say tighter tools. So for that comes the classical theory, which predicts that once the model can interpolate the training data, the test error should explode. So in practice, we see a second descent. After the interpolation threshold, test error falls again. So a parameterized network can still generalize. The reason is implicit regularization that keeps effective complexity far below the nominal VC dimensions. Now there are two practical routes replace pure VC analysis. First is algorithmic stability. If changing one training point changes the laws by O big O of 1 by n, the algorithm generalizes tightly. So stochastic gradient descent often satisfies this only. Then second is compression bounds. So if a trained network can be compressed to k bits without losing accuracy, the generalization gap is bound by the square root of k over n. So practical compressibility explains much by deep learning generalization. Okay. Then the master inequality is always the same. True risk is always less than equal to empirical risk plus complexity margin. So for finite classes, the margin is the square root of log of h over n. And for infinite classes, it becomes a function of VC dimensions. For modern over parameterized models, it is controlled by stability or compressibility. And generalization is the bridge that lets the machine that has only seen the past makes reliable statements about the future. So that was all about this architecture of generalization video, and hope you liked it. Thank you for watching. Bye bye.